In this section, we're going to take a look at how we can apply the properties of exponents to rational exponents. So in other words, we're going to move on from whole values as our exponents to using some fractions. It's all of the same properties. You have the product rule. The product property says if you multiply the same base, you're going to add your exponents. So if we have 5 to the 1/2 times 5 to the 3/2, remember the base does not change. So it remains 5, not 25. The base is 5. We add the exponents, 1/2 and plus 3/2 gives us 4/2, which equals 2. So then 5 squared is 25 for a final answer. We have the power rule. So if you have power of a power, you're going to multiply. So in this case, 3 to the 5/2 raised to the second. 2 times 5/2 gives you 5. So it's 3 to the 5th, or 243. Same would apply if you had multiple bases inside. So AB raised to the m, you have to distribute and do a to the m, b to the m. So in this case, 16 times 9 to the 1/2, you'd have to do 16 to the 1/2 times 9 to the 1/2. Remember that 1/2 means square root, so it's the square root of 16 times the square root of 9, so 4 times 3 gives us 12. Negative exponents still mean to take the reciprocal. So if you have 36 to the negative 1/2, that means 1 over 36 to the positive 1/2, which means the square root of 36. So you get 1/6 as your answer. Quotient rule, if you divide the same base, you're going to subtract your exponents. So 4 to the 5/2 divided by 4 to the 1/2. Well, 5/2 take away 1/2 gives you 4/2, which is 2. So 4 squared is 16. Same applies if you've got multiple things, different bases. In a quotient raised to a power, you're going to raise everything in the numerator, everything in the denominator to that power. So in 27 64ths to the 1/3, you do 27 to the 1/3, 64 to the 1/3. Remember the 1/3 power means the cube root. So the cube root of 27 is 3, the cube root of 64 is 4. So there's not anything new here. These are the properties of exponents we've looked at in Unit 0. Again, in later units, especially starting Unit 2, and now here in Unit 3, we're just taking a look at them when we don't just have whole numbers for exponents, but when we could have fractions as well. Okay, so we're going to use the properties of rational exponents in order to simplify each expression. If we have 12 to the 1/8 times 12 to the 5/6 power, we're multiplying the same base, so that's the product rule. And we need to add our exponents. The base remains the same, it does not ever change, so it's still 12. But I need to do 1/8 plus 5/6. Fractions require a common denominator in order to be able to add them. So I think about 8 and 6 and what their least common multiple is. And that would be 24. So I'm going to take 1/8 and multiply by 3 over 3 to get 3 24ths. And then I'm going to take 5/6 and multiply by 4 over 4 to get 20 24ths. So 3 24ths plus 20 24ths gives us 23 24ths. Our final answer, though, should always be in radical form. So that's the 24th root of 12 raised to the 23rd power. And the second one says 5 to the 1/3 times 7 to the 1/4. Well, 5 and 7 are different bases, so I cannot add their exponents. But I can distribute the cube, since both things are being raised to the 3rd power. So the power rule says I multiply my exponents. So I do 5 to the 1/3 times 3, which is 1, times 7 to the 1/4 times 3, which is 3/4. So 5 is the whole value, and then we have the 4th root of 7 to the 3rd power. Well, 7 to the 3rd power is 343. So it's 5 times the fourth root of 343. So again, number 3, we have different bases inside the parentheses, so I cannot add their exponents. All I can do is distribute the power inside. So I'll get 2 to the, well, 6 times 1/6 is -1. So 2 to the negative first times 4 to the negative first, which means they both drop to the denominator to get a positive exponent. So I need a placeholder of 1 on the top. So 2 times 4 gives me 8. Number 4, we have 10 divided by 10 to the 2/5. Remember, when something doesn't have an exponent, it means its exponent is a 1. The quotient rule says I should subtract exponents, so I'm going to keep my base the same. It does not change. So it's 10 to the 1 minus 2/5 power. Again, with fractions, to add or subtract, you need a common denominator. So I can express the 1 as 5 out of 5. So 5 out of 5, take away 2 out of 5, gives us 10 to the 3/5 power, or the 5th root of 10 cubed, which would be the 5th root of 1000. So if it's reasonable to figure out the power, we'll do that. In this example, it was 12 to the 23rd. That's going to be some massive value, so we'll just leave it written this way. Here we had 7 to the 3rd, very doable. Here we had 10 to the 3rd, again, very doable, so we figured it out. Number 5, we have 56 to the 1/4 divided by 7 to the 1/4, all raised to the 5th. Well, I'm actually going to do one of the properties somewhat in reverse, and I'm going to factor out that 1/4 power that they're both raised to, so that now it can be the 5/4 power here. Because if we take out the 1/4 and then the whole thing was being raised to the 5th, you multiply these, so you're going to have 56 over 7 to the 5/4. And now that I don't have any exponents in here, I can divide these. 56 divided by 7 gives me 8 to the 5/4 power. So that's the 4th root of 8 to the 5th, but 5 is bigger than 4, meaning I can take out an 8, because if it's to the 5th power, so you'd have the 4th root of 8 being multiplied 5 times, so it takes 4 of them to come out of the 4th root. So you can take an 8 out, and then you'd be left with the 4th root of that final 8. Number 6, you have 6 to the 1/2 times 4 to the 1/3 being squared. So I've got different bases, different exponents. All I can do is distribute in the squared. So I'll have 6 to the 1/2 of 2 is 1, times 4 to the 1/3 times 2 gives you 2/3. So you'll have 6 times the cube root of 4 squared. So 6 times the cube root of 16. But there's actually a cube root hiding inside of the 16. There's an 8 in there. 8 is 2 cubed, so you can cube root 8 to get 2 on the outside. So you'll have 12 times the cube root of 2. So the biggest question students ask me about these is, how do you know when you're done? The key is that your power should always be smaller than your index, otherwise you can simplify it. So here we had a problem because we were raising it to the 5th power, by taking the fourth root, which means you'd have 5/8 being fourth rooted, which is enough to take one outside, because a fourth root you need 4 of a kind. So you could take one out, and then you just have 8 times the fourth root of 8, because you always got to have a simplified radical. And that's also what happened over here. We ended up with 16 under a cube root, but there's a perfect cube in 16, and that perfect cube is 8. So we had to break it down into the perfect cube times whatever else. And we had to cube root this to get to the outside, multiply, and simplify. You should also never have any negative exponents when you're done. And, if it's reasonable to figure out, you should go ahead and figure it out. If it's going to be, too big and overflow even your calculator, then we can just leave it. But your final answer, if you've got a fractional exponent in the end, translate it back into the radical form. That's the formal way of writing your final answer. Here's an application problem. The ratio of the magnitudes of two earthquakes with magnitudes m sub 1 and m sub 2 as measured on the Richter scale is given by the equation r equals 10 to the m sub 1 power divided by 10 to the m sub 2 power. The table gives the magnitudes of some of the largest earthquakes that have occurred in the U.S. How many times stronger was the 1964 quake in Alaska than the 1812 quake in Missouri? Well, the 1964 quake in Alaska, pencil back, so it had a magnitude 9.2. The 1812 quake in Missouri was 7.9. So we're going to do 10 to the 9.2 power divided by 10 to the 7.9 power, according to this formula. Now, when we divide the same base, the base remains the same, and we subtract the exponents. So we're going to do 9.2, take away 7.9, and we'll get 1.3. So it's 10 to the 1.3 times stronger. If you plug that into a calculator, it comes out to be about 20 times stronger. Time for a key concept box. The properties of radicals. So just like the properties we studied for square roots, they apply for all radicals, whether it's cube root, fourth root, fifth root, whatever root it is. We still have the product property that says if you have a radical with the product underneath, you can split that up and take the radical of the first term times the radical of the second term. Same with the quotient. If you have a radical with a quotient underneath, you can split that up and take the radical of the numerator divided by the radical of the denominator. Let's take a look at some more examples. One more note to fill in before the examples. A radical with index n is in simplest form. If the radicand has no perfect nth powers as factors, and any denominator has been rationalized. Use the properties of radicals to simplify the expressions. Assume all variables are positive. So number 8 says the cube root of 12 times the cube root of 18. So we'll do the cube root of 12 times 18. And I could multiply those, but I'll get a large number, and I may not recognize the perfect cubes in that large number. So instead I'm going to break it down into factors. And I know that 12 is 4 times 3, and 18 is 9 times 2. And so I see right away, before I even break it down any further, I've got 9 times 3, which is 27. So I can think of this as the cube root of 27. And then 4 times 2 is 8. Well, those are both perfect cubes. The cube root of 27 is 3. The cube root of 8 is 2. So this is really just 3 times 2, or 6. Which tells me if I multiply this out, you'll get 216. And the cube root of 216 is 6. So 2 different ways of doing it. You can multiply it out right away, and then take the cube root. But if you're unsure if you're going to recognize that if something is a perfect cube or what its cube factors would be, you can always break it down into factors and take it from there. Alright, number 9 says the fourth root of 80 divided by the fourth root of 5. So I'm going to put it together as the fourth root of 80 divided by 5. So you get the fourth root of 16. Well, the fourth root of 16 is 2. Because 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay, so number 10 is just about simplifying to its simplest form. So I'm going to have to figure out what its factors are. It's 104, so I know 2 goes into it because it's even. 2 would go into it 52 times. Well, 2 goes into that as well. 26 times, so I can keep going one more time, and then I'll have it down to its primes. Well, and I've got the cube root, I've got 3 2's, otherwise known as 8. Cube root of that is 2. And then I've got my 13. So it's going to be 2 times the cube root of 13. Or from the very beginning, you could have seen, 8 goes into that 13 times. So you could have broken it down into 8 times 13. Cube root of 8 is 2. And then you have the cube root of 13. At this point, you should pause and try some practice problems before we go on to the final page of notes in this section, which is all about the practice problems. And just getting into some more complicated ones. Okay, hopefully you tried some of the beginning practice problems from either the textbook assignment or the worksheet before jumping into this page. I strongly recommend that you do so. This page just gets into all of the different cases of things you can come across. We're going to jump around a bit in order to take a look at each type of problem you could encounter and kind of build in difficulty. So we're actually going to start right here at number 18, where we have a quotient. So it says the sixth root of r to the 6th over s to the 18th. Well, the sixth root of r to the 6th, because we can split it up, over the sixth root of s to the 18th. Well, the sixth root of r to the 6th is just r. The sixth root of s to the 18th is just s cubed. Because if we wrote these as fractional exponents, it's r to the 6th being 6th rooted, so it's 6 over 6, and s to the 18th being 6th rooted, so it's 18 over 6. 6 divided by 6 is 1, and 18 divided by 6 is 3. My denominator is rational, meaning my exponent is a whole value, and I don't have any negative exponents or anything else that I can simplify, so that one's done. Then we're going to take a look at number 15, right above that. So it's the fifth root of 3/4. Unfortunately, this time it's not going to come out perfectly even. When I try and take the fifth root, it's 3 to the first, 4 to the first. So in fractional exponents, I have 3 to the 1/5. Over 4 to the 1/5. And that's the problem. I don't want to keep a fractional exponent in the denominator. In fact, I can't. I have to rationalize it. So before I begin rationalizing it, I'm actually going to break down the 4. 4 is 2 squared, so I can rewrite this as 2 squared to the 1/5. So you have 3 to the 1/5 over. I can multiply these exponents because it's power of a power. So I'm going to have 2 to the 2/5 power. And so then to rationalize, I'm going to have to multiply by a power of 2 in both the top and the bottom to maintain balance. I have 2/5, and I know when I multiply the same base, I need to add these exponents. So 2/5 plus 3/5 will get me to the whole value, which is what I need to have a rational denominator. So 3/5 is the exponent that I need on the power of 2 I'm multiplying by. In the top, we've got 3 to the 1/5 times 2 to the 3/5, all over 2 to the 5/5, which is just 1. So the numerator, I can't do too much other than see, hey, they both have a 5 in the denominator if they're exponents. They're different bases, so I can't add their exponents. But I can see that they're both being 5th rooted and put it back into radical form. So that's the 5th root of 3 to the 1st times 2 cubed, all over 2. So it's the 5th root of 3 times 8 over 2, or the 5th root of 24, all over 2. I know that I cannot break down 24. There aren't any 5th powers hiding inside of it, because 2 to the 5th power is 32, and we're under that. So it's the 5th root of 24 in the numerator, and the denominator is the whole value of 2. So it's been rationalized. So let's continue then to problem 11. In problem 11, you've got the 4th root of 10 divided by the 4th root of 27. So, 10 won't divide evenly by 27. They don't have any common factors. So I'm just going to go ahead and write them as fractional exponents. So it's 10 to the 1/4 over 27 to the 1/4. And 27 I can break down. That's a power of 3. So I'm going to think of it as 10 to the 1/4 over 3 to the 3/4. So that I can see to rationalize, I just need to multiply by 3 to the 1/4, because I have 10 to the 1/4 power over 3 to the 3/4. So I need the denominator to be a whole value power of 3. So I'm going to multiply top and bottom by 3 to some power, since I have 1/4, and I know that if I multiply the same base, I'm going to add the exponents. 3/4 plus 1/4 would get me to 1 whole. So I'll do 1/4 and 1/4. So I've got 10 to the 1/4 times 3 to the 1/4, all over 3 to the 1st power, because 3/4 plus 1/4 would be 1 whole. So then these are both being 4th rooted. So I can rewrite it as the 4th root of 10 to the 1st times 3 to the 1st, all over 3. So I'm going to get the 4th root of 30 over 3. Okay, so it's time for you to try one like this. So I want you to pause the video here and try problem 21. Then we'll look at our next type of problem we could encounter. So again, pause the video here, attempt problem 21. When you think you have it fully simplified, come back, restart the video and see how you did. Okay, so problem 21, you had a quotient of p to the 8th, q to the 5th being 7th rooted. So as fractional exponents, that's p to the 8 sevenths divided by q to the 5 sevenths. That's the problem. You cannot have a fractional exponent in your denominator. You need to rationalize, get this to be a whole value. So you're going to multiply top and bottom by q to the 2/7 power. So again, we're going to multiply by q to the 2/7 power because 5/7 plus 2/7 is 7/7. So p to the 8/7 times q to the 2/7, all divided by q to the 7/7, which is 1 whole. So the denominator is rationalized. Now I just gotta deal with the numerator. You don't really mess fractional exponents, and we've got to simplify because here the exponent's higher than the index. Because they're both being 7th rooted, so we can go back to the 7th root of p to the 8th q squared all over q. Again, I can't leave a p to the 8th under a 7th root. 7 goes in 8 one time, so I can take a p to the first out, and then there'd be 1p left over. So the 7th root of p to the first q squared over q. Number 19 is a quotient. They just started you out with fractional exponents, and we've got some different things going on. Start by dividing your regular numbers. 56 divided by 7 gives us 8. And then we deal with the a's. So this is an a without an exponent, meaning it's a to the first. A to the first divided by a to the 5/6. We have to subtract our exponents. So 1 minus 5/6. Well, 1 would be 6/6. Take away 5/6. Leaves you with 1/6. There's only one b. It's b to the 3/4 power. And then the c was in the denominator, but it had a negative exponent, meaning it needs to come up to the top and join everything else. We have c cubed. So now it's just a matter of making it formal, because I don't have any denominator left to rationalize. I don't have to simplify anything here because my numerator is smaller than the denominator, but I do need to find a way to write these in radical form. The 8 and the c are whole, so they're going to be on the outside. Got a to the 1/6 and b to the 3/4, so I got to find their common denominator so that I could write it as a single radical. Well, 6 and 4 both go into 12, so I'm going to rewrite it as b to the 2/12 times a to the 9/12. So I took this times 2 over 2 to get 2/12, and this times 3 over 3 to get 9/12, so that now I can write it as a single radical. Got my 8c cubed. Got the 12th root of b squared, 8 to the 9th. I know that's my final answer because I've got these whole values outside. I've got b squared, so definitely not enough to take a 12th root. I've got a to the 9th, not enough to take a 12th root. And I don't have a denominator, so I don't have to worry about rationalizing it. Alright, so let's move on from the quotient. Let's take a look at number 17. 17 says 32m to the 1/5 n to the, it says 32m to the 5th n to the 30th, all raised to the 1/5. So I got to distribute that 1/5, the 32, the m, and the n. So I'll have 32 to the 1/5 m to the, well, I multiply 5 times 1/5 and I get 1. N to the 30 times 1/5, 30 divided by 5 gives us 6. Now remember that 32 to the 1/5 power means the 5th root of 32. 5th root of 32 is 2. So it's 2m and the 6th power. The one right below it is very similar to this one, so let's take a look. It's problem 20. The cube root of 6x to the 4th, y to the 9th, z to the 14th. So the issue is that 9 is bigger than 3. We can't have that. It means this radical is not in simplest form. Same with 14. So we're going to break it down. I don't have a cube inside of 8. 2 cubed. I'm sorry, let me state that again. I don't have a cube inside of 6. 2 cubed is 8. So I can't break down the 6 at all, but I can break down x to the 4th, because 4 is bigger than 3, y to the 9th, 9 is bigger than 3, z to the 14th, because 14 is bigger than 3. So I'll leave my 6. I'm going to break down x to the 4th into x cubed times x, y to the 9th, well, that's y cubed times y cubed times y cubed, and z to the 14th, z cubed, z cubed, z cubed, z cubed, times a z squared, just so you can see how many times I'm going to be able to take a cube root. So the cube root of x cubed is x. This has to stay because it's not a perfect cube. This has to stay, it's not a perfect cube. But I can take out 1, 2, 3 y's. So y cubed, because y times y times y would be y cubed. 1, 2, 3, 4 z's. So it's z to the 4th. Inside has to stay this guy, along with the 6 and the x. So I have the cube root of 6x z squared. I know that's my answer because I've taken out all I possibly can. I don't have any denominators to rationalize. Another way to think of this, you could have turned them into fractional exponents, so 6 to the 1/3 times x to the 4/3 times y to the 9/3 times z to the 14/3. Well, then you're just dividing. So 4/3 is 1 and 1/3, meaning 1x could go out. Then you still have 1 under the cube root. 9/3 is really just 3. So you have a y cubed on the outside. 14/3 is 4 and 2/3, meaning you've got z to the 4th on the outside, and then you've got 2 left under the cube root. However you want to go through and think about it, whatever makes most sense to you is fine. Okay, let's take a look then at what happens when you've got sums and differences. Actually, there's one more like this to try. If you could pause the video and try problem 16, it's very similar to 17 and 20 that we just did. You need to break down the radical and get it into simplest form. So again, pause the video here, try number 16. When you think you've got it, come back to the video and see how it went. Okay, so we're just trying problem 16. It says the 4th root of 625 z to the 12th. Well, 625 is actually the 4th power of 5. I know it's a power of 5 because it ends in 25. Well, I can at least guess that it's a power of 5 because it ends in 25. And then if I check myself, 5 times 5 is 25, times 5 is 125, times 5 is 625. So I can take out the 5, and then the 4th root of z to the 12th, well, 12 divided by 4 is 3. So this is just 5z cubed. As fractional exponents, it's 625 to the 1/4 times z to the 12/4. Well, this you could, if you have a calculator, you could plug into a calculator, but you really just start to need to recognize and identify all of your powers, and 5 to the 4th is 625, meaning the 4th root of 625 is 5. And then here, we'll simplify that exponent. 12 divided by 4 is 3. So you get 5z cubed. Okay, now we're ready for the adding and subtracting. So problem 12 says 7 times the fifth root of 12 minus the fifth root of 12. You're actually ready to go ahead and subtract the way it's written because they're both fifth roots of 12. So the radicands have to be the same, the index has to be the same, and then you subtract your leading coefficients. So if you have 7 of them and you take away one of them, you're going to be left with 6 of them. So you have 6 fifth roots of 12. The radical is kind of like a variable. It's the same as if you had 7x, take away 1x, you'd be left with 6x. I know I can't break down the fifth root of 12 because 2 to the fifth power is 32, so there's not any fifth power inside of there I could take out. One right next to it, number 13, is very similar. I've got the same base, same exponent, so I can go ahead and add my leading coefficients. 4 and 8 gives me 12. 9 to the 2/3. Well, let's put that in radical form for our final answer. And actually, before I do that, let's break it down a little. 9 is a power. It's a power of 3. So I'm going to think of it as 3 squared to the 2/3, because 3 squared is 9. So if I do 3 squared to the 2/3, I gotta multiply 2/3 times 2, and I'll get 4/3. So I can see my power is bigger than my index. So I've got to take a 3 out to join the 12. So I've got to do 12 times 3 times 3 to the 1/3, because 4/3 is 1 and 1/3, so we have 3 to the first times 3 to the 1/3. Well, 12 times 3 is 36, and then we've got the cube root of the extra 3. So our final answer here, our simplified formal final answer, is 36 times the cube root of 3. When we get to problem 14, we've got a little bit of trouble in that we do not have a matching radicand anymore. 81, 24, not the same. We do have cube roots that are the same, so that's good. But we've got to break down the 81 and 24. So I know that 81 is 3 to the 4th power, because it's 9 squared, and 9 is 3 squared, so it's 3 to the 4th. And 24 has an 8 and a 3 inside. So I can think of this as 3 cubed, or 27 times 3. Minus the cube root of 8 times 3. Cube root of 27 is 3 times the cube root of 3. Cube root of 8 gives us a 2 on the outside, times the cube root of 3. And now our radicands match. Our index is the same, so I can subtract leading coefficients. 3 take away 2 leaves us with 1, so it's 1 cube root of 3. Alright, so I would like for you to try problems 22 and 23. So pause the video here, try problems 22 and 23, then come back, press start, and see how you did with them. Okay, so we're trying problems 22 and 23. On problem 22, we've got a to the 4th, b to the 2/3. So that all matches. We can go ahead and add the leading coefficients. So 15 plus 8 gives me 23, 8 to the 4th, b to the 2/3. And then the only thing I have to do is write this in radical form to have a formal final answer. Because I don't have any denominators to rationalize, I don't have to simplify my radical because it's b squared under a cube root, so the power is smaller than the index. So that can be my final answer. Number 23 says 10 times the 4th root of 5 times 7 to the s power minus s times the fourth root of 80 times s to the third power. So I'm not ready to subtract yet because my radicands do not match. I've got the fourth roots, I've got a variable outside here, I don't have a variable outside there, and these radicands aren't the same. So I start to simplify. The issue with the first one is the s to the seventh. I can't have a seventh power under a fourth root, so I'm going to break it down into s to the fourth times s to the third, because 4 plus 3 is 7, so this is the equivalency of s to the seventh power. It's just now I can see, oh, I have a fourth root, I have a fourth power, excuse me, I'm trying to take a fourth root. Second one we have s times the fourth root. 80 I gotta break down. I gotta think about what fourth power is inside of 80. It's 16. 16 times 5 is 80. S cubed is not going to be able to simplify because 3 is smaller than 4. So now I start to break things down. The fourth root of s to the fourth is s, so it's going to come out with the 10. Then I have the fourth root of the 5s cubed minus the fourth root is 16, so that is 2, so that comes out with the s. And then I have the fourth root of 5s cubed. So we've got 10s, take away 2s, so we're left with 8s times the fourth root of 5s cubed. I know I'm finished because I don't have a denominator to rationalize. I broke down this fourth root as much as I can. There's not a fourth power hiding inside of 5 or s cubed. My radicands matched, same with my variables on the outside and my index. So I was able to just combine them. If I had 10 of them and I take away 2 of them, I'm left with 8 of them. Remember, think of this whole thing as a variable. It's just going to stay the same. You're just changing the 10, take away 2 to be an 8. Okay, folks, so those are all the different types of problems, for the most part, that you can come across. Some good examples there. Now it's just time to practice, practice, practice. Nothing new in this section, just taking what we knew previously about the properties of exponents and simplifying radicals and applying it in more complicated situations.